All right, so this is the first part of section 1.3. 1.3 is all about how we can use numerical values to describe our quantitative data. So in 1.2, we looked at how we could graph quantitative data, remember, with the dot plots, the stem and leaf plots or stem plots, and histograms. We also talked a little bit about shape. Now, we mentioned in class that the purpose of shape was to give us an idea as to what the overall pattern of the set of data looked like. We also talked about some of the unusual features, possibly some outliers, gaps within the data, and those are two very important things to think about when describing a distribution. However, we also need to talk about how we can measure the center of the graph as well as the variability or spread of the distribution. So both of these serve a specific purpose. The purpose of measuring the center or finding the center and describing it is to give us an idea as to what a typical value in this set of data looks like. So in general, there are three measures of center, which are the mean, the median, and the mode. Now, we don't use the mode very often other than to describe the peaks of the distribution, like we mentioned, the unimodal, bimodal, and multimodal aspects of a graph. When we actually want to talk about the typical values or the center, what we focus on is the mean and the median. So as you should know from previous classes you've taken or things you've done, the mean is simply the actual arithmetic average of all the individual data values. And so if you wanted to find the mean of a set of observations, you're adding all the values and dividing by the total number of data values. Now, in statistics, we're given a formula to calculate the mean, which really does nothing more than what we said we were going to do. The formula says that if you have n observations, call them x1, x2, all the way to xn, then the mean of your sample, which is notated as an x with a line over top, pronounced as x bar, is found using the formula, which is describing exactly what we said. The sum of your data values over the number of data values. So you have, in the sum of the data values, you have your sigma. So the Greek letter sigma right here on the top represents sum of. Hopefully you knew that from another course. So the sum of all the x's divided by n. Okay? So that's one measure of center, gives us an idea of a typical value in the set of data. Another option is to look at the median. And so the median in a set of data is the midpoint of a distribution. The number so that about half of the observations are smaller and about half are larger. So if you wanted to find the median, then you would start by arranging your data values from smallest to largest. And then basically you're searching for the center, just like you've done in the past. So if you have an odd number of observations, then the median is the middle value in that ordered list. So you would find the number exactly in the middle. If the number of observations happens to be even, then you're using the average of the two numbers in the middle. So halfway between the two numbers in the middle, once you've got your list ordered. Now, I mentioned that we were talking about the sample mean. So the values that we're looking at calculating here are what we call statistics. And so a statistic is a number that describes some characteristic of a sample. Everything we're focusing on right now is going to be a statistic, a characteristic of a sample. If we were referring to that same characteristic of a population, then we would call it a parameter. And our parameters have different notation than what we're talking about here. So for example, the sample mean is the x bar that we mentioned above. So the sample mean would be x bar. Oops. Now, if we're talking about the mean of an entire population, so the parameter would be mu. Let me redo that one. That did not come out so well. Okay, it's the Greek letter mu. Again, a statistic comes from a sample. A parameter comes from a population. So some of our statistical measures are going to be what we call resistant. So what does it mean to be resistant? So a statistical measure is resistant if it is not sensitive to extreme values. So if a number that's really far away from the majority of the data doesn't affect the measure, so if it doesn't affect the mean or the standard deviation or the IQR, the range, whatever it is we're looking at, we would say that that measure is resistant. It's important for us to note that the mean is not resistant. Okay, the mean is not resistant to extreme measures, where the median is much more resistant to extreme measures. So if a distribution is roughly symmetric, the mean and the median have about the same value. The distribution is skewed, the mean is usually farther out on the tail than the median. The mean gets pulled into the tail of the distribution, where the median kind of stays close to where it was. So again, these measures of center are giving us an idea of a typical value. Now, the next thing we need to think about is a measure of variability or spread. So how consistent are the numbers? Are they really close together? Are they more spread apart? Are they more variable? Do they change more? Okay, so we have basically three ways that we measure variability. One is something you should be familiar with. So the first thing we talk about is the range. The range of a distribution is nothing more than the difference between the maximum and the minimum values. So the difference between the largest value and the smallest value. So the range would simply be found by taking the maximum and subtracting the minimum. So now this isn't a really great measure of variability or spread, because the range is definitely going to be affected by any outliers. So it's not resistant to outliers. If our maximum or minimum value happens to be an outlier, then it would cause the range to be a very large number. Okay, so if our maximum or minimum is an outlier, then the range is a very large number. One of the better measures of variability that we use is called the standard deviation. So a standard deviation measures the typical distance in a distribution from the mean. So typically, how far do these values vary around the mean? Are they really close to the mean, or are they farther apart? So the standard deviation is calculated by finding the average of the squared deviations and then taking the square root. That initial average of the squared deviations that we're talking about is called the variance. So here's the formula for variance. We're going to go over this in class when we work on some questions. So just have the formula written down. And this is, of course, a sample variance. So sample variance means it's a statistic. It's coming from the sample. The notation is S with a subscript x squared. This is the variance. It's the squared deviations from the mean averaged. If we want to find the sample standard deviation, we take the square root of that variance. So the steps for calculating the standard deviation are, number one, you find the mean of the distribution. Once you have the mean of the distribution, calculate the deviation of each value from the mean. So you take the value and you subtract the mean. How far is the value from the average? Square each of these deviations. Then we add all of the squared deviations and divide by n minus 1 to get our sample variance. If I want to get the standard deviation, I take the square root of that sample variance. Now there are a couple properties to keep in mind when dealing with the standard deviation. So the standard deviation, noted as S subscript x, measures the spread about the mean and should only be used when you've chosen the mean as your measure of center. Your standard deviation always has to be a value that's greater than or equal to 0. it should only be equal to 0 when there's no variability, which would mean that all of the observations have the exact same value. Otherwise, your standard deviation has to be greater than 0. As the observations are more spread out, the standard deviation gets larger. The standard deviation is going to have the same units of measurement as the original observation. Variance is always going to be squared units of measurement. And so that's why we usually turn it back into a standard deviation, the square root, so that we have the exact same units of measurement that we started with. And of course, because the standard deviation is dependent upon the mean, it is also not resistant. So outliers or strong skewness can cause huge effects on the standard deviation. They can make the standard deviation much larger. Okay? And then the last measure of variability or spread that we use is what we call the interquartile range, or in short, the IQR. So the interquartile range is based on quartiles. So first thing we need to know is what exactly is a quartile. So a quartile is basically values that divide the set of data into 4 pieces. Okay, so you have your ordered data and the quartiles divided into 4 even groups with about the same number of values in each group. So to find the quartiles, you order the data from smallest to largest, just like you did with the median. You find the median, and then you take the lower half and find the center of the lower half, take the upper half and find the center of the upper half, or the median of the upper half and the median of the lower half. So that first quartile is the median of the data values that are to the left of the median in the lower list. So it's the median of the lower half of the data. Your third quartile is, on the other hand, the median of the upper half or the right half of the ordered list. The interquartile range, which is the actual measurement of variability or spread, is simply the difference between the first and third quartiles. So in symbols, the IQR is equivalent to the third quartile, Q3, minus the first quartile, Q1. So where the standard deviation tells us how far values are on average from the mean, the IQR simply gives us the range of the middle half or the middle 50% of our distribution. So it's just giving us an idea as to where the middle half of our distribution is located, how far apart these values are. So important to note that the quartiles and the IQR are resistant measures of spread. The range and the standard deviation are not resistant. They are greatly affected by outliers and skewness. Important. Any useful description of numerical values in a distribution requires both a measure of center and a measure of variability or spread. The most common descriptions are a combination of the mean and standard deviation for center and spread. That's typically what's used to describe the center and spread. Now, it's not always the best choice, although it is typically what's used. The best choice is going to be dependent on what your graph looks like, its shape. So if the distribution of the data set is roughly symmetric, the mean and the median will be similar. If the distribution is skewed to the left or skewed to the right, then the mean is going to get pulled in the direction of the skew. So when our distribution is roughly symmetric, we go with the better measure of center and spread, which would be the mean and the standard deviation. Okay? If the distribution is skewed, then we use the median and the IQR because these two values are resistant. So they're not going to get pulled as far into the tail, or the median is not going to get pulled as far into the tail as the mean would. And so because we've chosen the median, we would then choose the IQR as the measure of variability or spread. So we should remember, the graph gives us the best overall picture of the distribution. The numerical values for center and spread are giving us specific facts about a distribution, but they don't describe its shape. The numerical summaries are only highlighting key features. They're not telling us anything about the peaks or any clusters or gaps. So it's super important that we always plot our data. So in the next video, the second part of this section, we'll take a look at how we can generally figure out where outliers exist. We'll look at a fourth graph that can be used for quantitative variables. And then finally, we'll talk a little bit about comparing two distributions. Thanks.